All right, good afternoon again, Principles of Engineering. Today we are working on work, energy, and power. This is the unit that follows up our electrical circuits. So it is 1.2.4, I believe. So we're going to go through that today. If you have any questions, once again, if I'm at officer training school, I will not be able to answer any emails, or if I do, it'll just be like by luck. So reach out to the sub, and then I'll probably get a chance to get them some resources to answer questions that you guys may have. So to start, work, energy, and power. If you look for this, it is on your in your canvas underneath 1.2.5. All right. We are going to do the simulation for this assignment instead of the actual one. All right. So make sure you're in the simulation link, not the real world one. All right, so work, energy, and power. To start, work is the energy transferred when a force, F, is applied to an object moving through a distance, D, the lowercase d. So work equals force, and in this case, force has to be parallel to the distance the object moves, okay? Meaning that if the force goes this way, it has to move a distance of that way. It has to be parallel, okay? And for the purposes of this assignment, we're going to use the metric system. So we have SI units of work, all right? And we have 1 joule. 1 joule is equal to 1 Newton meter, all right? So here we have an example. A student lifts a 50-pound ball 4 feet in 5 seconds. How many joules of work did the student complete? All right, so we have our work equals force times distance. The force being, well, they have to exert 50 pounds to lift 50 pounds. So force, 50 pounds, times the distance of 4 feet. Okay? 50 times 4, and it's 200 foot-pounds. Okay, this is an amount of work. However, it is not in the SI unit of joules. So we need to make sure we do our conversions. Okay, so how many joules of work did the student complete? So we have to convert to joules first. So in this case, and if you guys look at your formula sheets, this formula is in your formula sheet, and is 1 Newton is equal to 0.225 pounds. Or your conversion factor is 1 Newton over 0.225 pounds. So we multiply 50 pounds over 1. Okay, your pounds cancel out. And you get 50 times 1 over 0.225, and that gives you 222.5 newtons. Okay. We also have to convert our feet into meters because we're using metric. Okay. So we have 4 feet multiplied by, and once again, this formula is on your formula sheet, 1 meter over 3.28 feet. All right, the feet cancel out. 4 times 1 over 3.28, and you get 1.22 meters. Okay, so now we have our force and we have our distance. So once again, 222.5 newtons times 1.22 meters. Okay, and once we put those together, you get 271 joules. All right, and how do we know that's joules? If we go back again, remember, 1 joule is equal to 1 Newton meter. So 271 Newton meters is 271 joules. Okay, so let's look here now. The ability to do work. And these are just some definitions. Once again, there will be vocab, so you guys need to understand that. But energy is the ability to do work. So energy can be through a variety of things: light, heat, mechanical, chemical, electrical. All forms of energy can be used to exert a force for a distance. So roller coasters, NASA solar sails, fuel cells, all examples there. All right, and then you have different types of energy. You have potential energy. All right, so that's stored energy. So think water at the top of a dam. A roller coaster, as it's climbing the lift hill, is going to gain potential energy. All right, potential energy. Kinetic energy is when energy is which a body possesses because of its motion. All right, so the windmill moving. All right, the water actually going through the dam and causing the turbines to rotate, the space shuttle taking off, the roller coaster going down the hill, all kinetic energy. All right, now we can transform energy. So for example, we have chemical to kinetic. So people eating food, that food is then used to create kinetic energy. All right, radiant energy. All right, that's the sun creating chemicals. All right, electrical energy then being used to turn it into heat energy. All right, so we can transform the type of energy, but we can't do it without any loss. Now we have different types of renewable energy sources, biomass, so like think of E85, things like that, hydropower, dams, geothermal, so using the heat of the earth to for HVAC systems, wind turbines, solar power, all different types of energy sources. All right, and those are our renewable. All right, so we can reuse them. It's not going to cause any issues. We're not expending a resource to use it. Okay. Non-renewable is something that we cannot replace. So coal. We only have so much coal in the world. We only have so much natural gas, petroleum, uranium. All right, there's only so much of it. Conservation of energy. So energy cannot be created or destroyed. All right, that's just a basic law of energy. You cannot create or destroy it. You can only change it from one form to the other. However, whenever we change the output energy, we're going to lose that, and usually it's from heat energy. All right. So here's some example of conversions for making electricity. Fossil fuels, chemical. So we burn fossil fuels to create heat. The heat warms up the water. The water turns into steam, turning the turbines. The turbines then create electricity. Okay, so that's one example. Wind turbines, they turn a generator, which creates electricity. Okay, all these are examples. Okay, so we also want to figure out the efficiency of our system, and just like our efficiency calculations for simple machines, it is the energy out divided by the energy put in multiplied by 100%. And that will give us our total efficiency. What are current energy concerns? So as an engineer, what are things that we are looking out for? So consumption, pollution, depletion, dependency on natural resources, the cost. All right. Here's the graph from the EIA.doe.gov. All right, based off of our consumption, as you can see, petroleum being our highest, and that is a non-renewable. So while there's still quite a bit of petroleum left, there is initiatives to try and move towards things that are non-renewable, such as wind and solar. All right. But we'll see where we go with that. Some other formulas to keep in mind. Power. To calculate power, it is power equals E, this E standing for the energy expended, and then over T being time. So how much energy is expended over time, or P equals how much work is performed over time. All right. And if you remember, you might end up finding work again. If we go back to our electrical things, electrical PowerPoint from last lesson, it was power equals I times V, right? So you might end up using that later on, just to little note there for you. All right, the metric unit for power is the watt, okay? And 1 watt equals 1 joule per second, okay? Don't get watt confused with work, okay? Just depends on where we're at. Some other types of power. Once again, we have electrical power, uses electrical energy to do the work. Mechanical, so linear rotary motion. Fluid power, so hydraulics and pneumatics, which we will get into later in the year. All right, here's a power example. Student lifts a 50-pound ball, 4 feet, 5 seconds. How many watts of power did the student use to lift the ball? Remember, 1 watt equals 1 joule per second. Earlier, right, we already calculated how much work was done. 271 joules, right? 271 joules. We already figured that out from the initial problem. So we know how much work was done. The work equals 271 joules. All right, we have some other information though. 5 seconds. How do we figure out what? Joules per second. So 271 divided by 5, right? Because that's how much work was done in 5 seconds. And that should give us the amount of watts. Okay? So 271 divided by 5, all right? And you get 54.3 joules per second. 54.3. Because P equals W over T, 271 divided by 5. Easy peasy. And once again, 1 watt equals 1 joule per second. So you have 54.3 watts. Boom. All right. Keep in mind, I cannot answer emails probably. All right. I'm not going to say I won't, so you can send them. If I have the ability to answer, I will. Otherwise, please contact your sub. Another good person to talk to if you are not understanding would probably be one of our teachers down in the science department. If you talk to Mr. Ornstein or Montgomery, they would probably be able to help you with this, I'm sure. So with that being said, that's the PowerPoint. Now, once again, make sure you are in activity 1.2.5 Mechanical System Efficiency, SIM. All right, there are 2 of them. Okay, we'll go back here, that way you can see them. Okay, I don't want you guys to get confused. All right, oh dear, my goodness. What is going on? All right, so we'll go back to the home page. Course content. Where were we? Energy sources 1.2. And we are on, here we go. So you have 1.2.5 VEX. We are going to do activity 1.2.5 SIM. All right. So make sure you're in that. And once again, it shows our efficiency calculations. You guys are going to use basically a calculator. And in this activity, you will investigate the energy conversion systems designed to change electrical energy into mechanical energy. So given an ATV, or all-terrain vehicle, winch data, you're going to determine the efficiency of the system under various loads. Remember units and precision when recording your data. All right. ATV winches pull a horizontal load during testing. Make sure you guys read this. Here's your forces. Here's your distance. Isn't it nice? They already put in Newton and meters for you guys. Fancy. All right. Go through this. If you guys have questions, once again, talk to the sub. But read your instructions. And then you will submit that to the sub for grading. So other than that, have a good day. Good luck. I'm sure you all do fine. Very good.